Let's do the following questions in preparation for your long test 3. Okay, first question. Which of the following expressions exactly represents the sequence below, assuming the pattern continues? So here in this problem, there is no formula that you could follow, but to solve this, you just have to look at the pattern. You have to examine the pattern by comparing the term from the previous term. So as you could see here, from 4 becomes 9 over 4, then 16 over 9, then 25 over 16. Now, notice that the numerator are all perfect square and the denominators as well. And this is the same as that. This number is the same as this number, and then 25 is the same as that number. Okay, so this denominator here, that is actually 2 squared. And the numerator is also 3 squared. Then that means 4 squared. 16 is 4 squared. Denominator is 3 squared. Then the numerator is 5. That's 25 is 5 squared. 16 is 4 squared. And also 36 is 6 squared. And 25 is 5 squared. And so on. Now, looking at this pattern, you see that the base actually increases in the increment of 1. So if this is your n, that becomes n plus 1. Okay, and then also the numerator is the same as this. So how do we, do that? So if you compare the numerator with the denominator here, this is 3 and that is 2. So the numerator is greater than the denominator. So because of that, we suspect that the pattern is like n plus 1 n in the numerator, and then, or it could be n plus 1 in the numerator and then n in the denominator, and they're both squared. Okay, so now let's look at the choices here. Do you see n plus 1 squared over n squared? And then now you look at the counter here. Okay, so it looks like this is the answer, but don't immediately pick it because you have to look at the counter as well. Here it starts at n equal to 2. So starting at 2, so this is greater than or equal to 2. So if you start at 2, you would have 2 plus 1, and that is 3. And then the denominator is 2. What about the first term? How do we get that 4? So if you start at n equals 2, this would not work because the first term here is not, you won't be able to actually get that. So it's not part of that series or sequence. Now that 4, you could write that as 2 squared over 1 squared. So again, since the n here starts at 2, then this won't work. Now let's try to manipulate this expression here so that one of the choices here would work. So what we notice is that the numerator is 1 greater, the base in the numerator is 1 greater than the base in the denominator. That means that if I can have my numerator as n minus 1, then I can have n in the numerator. So if my base in the denominator is n minus 1, then the base in the numerator would be n. So those two are just equivalent. Then which one would that be? Letter C. So now let's see if this works. So here n starts at 2. So if n is equal to 2, 2 minus 1 is 1. So that gives you 1 squared. If n is equal to 2, you will have n squared, 2 squared. So that's the first term. Okay, so that means that letter C is the answer. Letter C is the answer because here n is greater than or equal to 2. And then you can go ahead and plug in n. So we already plugged in n equals 2. Now you can try n equals 3. So if n is equal to 3, you will have 3 squared in the numerator, and then 3 minus 1 is 2, 2 squared in the denominator, and so on. All right, so this works. That is the sequence only if n is greater than or equal to 2. This could also be an answer, but here n needs to start at 1. So this could be the representation, but n needs to be greater than or equal to 1. That's why this won't work. Number 2, we are asked to find the nth partial sum of the series. That means you're going to find S sub n. So to do this, we will need to expand this sequence or this series here. So you just have to expand that. That means you have to plug in starting at n equals 1. So you will have 1 over ln of 3. So 1 over ln of ln of, so n equals 1. So 1 plus 1 is 2, ln of 2, minus 1 over ln of 3. That is when n is equal to 1. Now next, when n is equal to 2, so this is the case when n is equal to 1. So next, when n is equal to 2, you will have 1 over ln of 3 minus 1 over ln of 4. So this is the case when n is equal to 2. Plus 1 over ln of 4, that is when n is equal to 3, minus ln of 5. This is the case when n is equal to 3, and so on. Then you look at the pattern. Here you notice that, okay, so let's just write first the nth term. So until you reach that part, which is ln, where would I write that? 1 over ln of n plus 1 minus 1 over ln of n plus 2. Okay, so that is the series here. Now, notice that this term here cancels with that term. The term cancels with that. This suggests that the inner terms actually just cancels out. And what would remain will be this term here, which is the first term. So that is 1 over ln 2, and then the last term, which is 1 over ln of n plus 2. And that is your S sub n. That is the sum of the first n terms. Okay, and what is that? That is the first choice. Okay. Next number, we are to find the limit of the sequence with the given nth term using the L'Hopital's rule. Your A sub n is equal to n to the 1 over ln n. Now this could also be the solution when you're asked to determine whether your sequence is convergent or divergent, or whether the series is divergent if you use the divergence test. When you use the divergence test for the series, all you need to do is take the limit of your A sub n as n approaches infinity. Or if you want to know convergence, divergence of your sequence, you also take the limit of that of A sub n. Okay, so you could also see that as, a question that relates to this number here. All right, so let's go ahead and find the limit of A sub n here. And notice that this n to the 1 over ln n is actually an indeterminate of the form. This is of the form infinity over 1 over infinity, and 1 over infinity approaches to 0. So that is of the form infinity to the 0, which is indeterminate. Now, then, using L'Hopital's rule, we actually use the property of Ln, which is, if you remember, e to the ln x is equal to x. So here, we would just have to raise this to, so this expression that n to the 1 over ln n, you just have to write that as e to the ln of n to the 1 over ln n. And then you apply the property here, for logarithm, that you could actually bring down the power here to here. Okay, so that's the power rule. So this is equal to e 1 over ln n times ln n. Now what you notice, you actually have that. You can cancel ln n, and this just equal to e, right? So that, therefore, if you take the limit of this expression, of the expression here, that is n to the 1 over ln n, so it's just a constant, right? And n approaches infinity, but we found out that this expression here is just actually equal to e. So this is just equal to limit n approaches infinity of e, and limit of the constant is also constant. So therefore the limit here is just equal to e. For this next question, we are to determine if this series is convergent or divergent. And if it is convergent, you are asked to find the sum. Now, if you are asked to find the sum of the series, that means that your series is either a geometric series or a telescoping series, right? Because those were the only two series that you could actually find the sum. The rest, you can just determine whether they are convergent or divergent. So here it is, you are asked to find the sum if it is convergent. So that suggests that this series is actually a telescoping series. So to eliminate the process that this one is not divergent, you will have to use the divergence test first. Okay, so check for divergence first. So you just need to check first for divergence. That is what you need to do if you are given a series. And to do that, you are just going to take the limit of 1 over n squared minus 1, so the limit of a sub n as n approaches infinity. Now, if you get a 0, that means it's not divergent. Okay, that means it's inconclusive. Not divergent, that means it doesn't mean that it is convergent, all right? So here, if you plug in infinity, here, so you will have 1 over infinity, and that is actually 0. Constant over infinity is 0. So that means this is not divergent. Divergence test failed. Okay, so it could either be divergent or convergent, but it fails the divergence test. So that means that there's a possibility that this series here is convergent. So we suspect that this series here is a telescoping series. That's a telescoping series. And now, how do we verify if this is indeed a telescoping series? We can write that a sub n, which is, let me write that here, 1 over n squared minus 1, you could write that as 1 over n plus 1 times n minus 1. You could factor that out. And this is equal to n plus 1, numerator a, plus b over n minus 1. Now you remember, okay, so we're doing partial fractions here. We are rewriting 1 over n squared minus 1 into partial fractions. So we are to compute for a and b. Okay, so this is equal to a times n minus 1 plus b times n plus 1 all over n plus 1 times n minus 1. And then you equate the numerator. You will have 1. You equate this to that. Then you will distribute this. So this is equal to an minus a plus bn plus b. So that suggests that a plus b, so this is equal to a plus b times n minus a plus b. So by comparing of coefficients, we know that a plus b is equal to 0 because there's no n here. And then the constant, the a, negative a plus b is equal to 1. Then you can solve for the system here simultaneously. If you add the two systems, you will have 0 plus, so you will have 0 plus 2b is equal to 1. So that means that b is equal to 1/2. Now from here, it means that both of them are equal, but the signs are different. Okay, so a is just equal to negative b. So a is equal to negative b. Hence, therefore, our series, so that series there is just equal to 1/2. Oh, let me just write that down. Summation of, then you plug in your a here. So a is negative 1/2 over n plus 1 plus, and then your b is 1/2 n minus 1, n starting at 2 to infinity. Okay, so you can also rewrite this. You could take out the 1/2. Let's take that out. I can have 1/2 here, starting at 2 to infinity. Now I could interchange this too, because this one becomes a negative term. So that is also the same as 1 over n minus 1. Oops. And then minus, okay, I just interchanged the two terms. Okay, because we know telescoping series, the second term is negative. And that is 1 over n plus 1. Right, so this is, and then both of them is multiplied by 2. Now, okay, we need more space, but you know, that's the idea. So now we're able to write it this way. Now next is to expand it. Okay, so let's try to expand this to see what S sub n is. Okay, so let's compute for S sub n. And then after that, we will take the limit as S sub n approaches to infinity. So you have 1/2, and then you plug in the values. You start at n equals 2. So that is 1 over 1, the first term, minus 1 over 3, plus 1/2 minus 1 over 4, plus 1/3 minus 1 over 5. Again, how did I do that? I just plug in the values for n. This is what you get when n is equal to 2. So you start at the counter here. So starting at 2, 2 minus 1 is 1. Now 2 plus 1 is 3. And this is when n is equal to 3. Now if n is equal to 3, 3 minus 1 is 2. 3 plus 1 is 4. Then this one here is when n is equal to 4. So n, which is 4, 4 minus 1 is 3. So you have 1/3 minus 4, 4 plus 1 is 5, and so on. Then you look at then you write the last term. Okay, so what would be the last term? So that would be the nth term. That would be n minus 1 plus 1 over n plus 1. So what do you notice here? You notice that this term here, so before that, we will have to write down the first few, okay? So we will have n, so that is n, if n is n minus 1, this will be n minus 2. That would be n minus 2 plus 1 over n, 1 over n. This is the case when n is equal to n minus 1. And then plus, I'll just use k, because you might get confused if I have the same n here. That is just notation, but I'll just have k. So this is when n is k minus 1. Okay, k minus 1. Now, lastly, we will consider when n is equal to k. So we're looking for s of k. So you will have 1 over n minus 1, or k minus 1, k minus 1 minus 1 over k plus 1. Okay, that's a lot easier to see it this way. So what do you notice? We notice that what cancels, so which one cancels out? The 1/3 here cancels out with that. And then your 1/4 would actually cancel. We should have to have another one. We know that actually if n is equal to 5, you will have 1 over n minus. So if n is equal to 5, you will have 1 over 4 in the next term here. So if you add more term here, if n is equal to 5, because this is n equals 4. But when n is equal to 5, you will have 1 over 4. So that would make this cancel. So that term would also cancel, and so on. So that's the pattern. So what we're interested at is to find the expressions where it doesn't cancel. Now for the last part, okay, the last part here, we would have to, determine which one will not cancel, right? So we feel like definitely the other one, this one won't cancel, right? That one won't cancel. And which term here didn't cancel? The minus, the 1, and then the 2. Okay, so this and this one won't cancel. Okay, so this and then that cancels. Now, but if you take the limit, okay, so let's take the limit. So to get s, here, I'll just have the solution here. So to get s is just equal to the limit of s sub n as n approaches infinity. So this would be our s sub n, You just change the k to n. So we will have, you have the 1/2, and then you have 1 plus the 1/2, and then plus, say we thought 1 over k won't cancel, plus, minus 1 over k plus 1. Then, if you take the limit here as n approaches infinity, this just goes to 0, and that goes to 0 as well. So you're left with the number here. So that means 1/2 times 1 plus 1/2 is 3/2. So that gives you 3/4. Right? So that means it is convergent because we get a number that is greater than infinity. So that means it is convergent. So the series is convergent and the sum of the series is 3/4. That's for number 4. Okay, now for number 5, let's look at number 5. Determine if the sequence a sub n given by this is convergent or divergent. If it is convergent, find its limit. Okay, so here we're just looking for the sequence. So to determine, we're just given a sequence here. To determine whether a sequence is convergent or divergent, all you need to do is find the limit. Okay, find the limit as n approaches infinity. Now, if the answer is infinite, that means it's divergent. If the answer is a constant, that means it's convergent. Okay, so let's take a look at the limit. Limit of a sub n, so that's the square root of 2n squared plus 1 all over n as n approaches infinity. So now you take the limit here. So how do you find the limit? You can just 2n squared plus 1, multiply that by 1 over the square root of 2n squared. Your goal is to actually cancel this. Your goal is to be able to cancel this. And so you do the same thing in the denominator as well. So you will have n times 1 over 2 square root of 2n squared. Now, what do we know? The square root of n squared is actually the absolute value. Okay, that's actually the absolute value of n. So just remember, change the color of the pen. So remember the square root of n squared is not equal to n, but rather that's the absolute value of n. Okay, so that means that for the numerator, for the limit, n approaches infinity, and that, because this is a square root, you could put this inside. Okay, so that gives us the square root of 2n squared over 2n squared is just 1 plus 1 over 2n squared. Okay, and then the denominator will be n over square root of 2 and then absolute value of n. Now, since n approaches infinity, for absolute value, if it's positive, then you get positive. So this is equal, what is the meaning for absolute value? That is equal to n when the values are positive, and that's also equal to negative n when the values of n are negative. Okay, because the absolute value always gives you a positive number. So this is equal to the limit n approaches infinity of 1 plus 1 over 2n squared all over, that is just, this one will just be replaced by n. So that means that is just 1 over square root of 2. 1 over square root of 2. Okay. Now, this goes to 0. That goes to 0. So you're left with 1 over square root of 2. 1 over square root of 2. And that gives you square root of 2. So it is convergent to square root of 2. Now let's consider the next problem. For this given series here, which of the following statements are true? Then you have to check whether the series is convergent, converges absolutely, converges conditionally, and the series is divergent. Now, when you are going to do something like this, or when you're given a series, your first step is to determine whether your series is divergent. So you do the divergence test first. Okay, so divergence test. Let me look at the divergence test. Now, when you say divergence test, you have to determine the limit of a sub n as n approaches infinity. You just want to make sure that the answer is not 0. If the answer is 0, there's no conclusion. If the answer is not 0, it is divergent. Okay? So divergent if the limit is not 0. So divergent if the limit of a sub n is not 0. So you go ahead and do that. So go ahead and determine whether the series is convergent or divergent. Whether the series is divergent using the divergence test. Okay, so take the limit n approaches infinity of n squared minus 3n all over square root of n to the 5th plus 2. So as a shortcut here, you can actually, you can compare this to get the leading term in the numerator and also the leading term in the denominator. So you just do this, limit n approaches. This is just the shortcut. If you are not asked to show a solution, you could use this. Okay, so this one, get the leading term in the numerator, n squared over square root of n to the 5th. And then you simplify that. So when simplified, square root of n to the 5th is just equal to n to the 5/2, so that is 2.5. So that means that if you use loss of exponents, so this is just limit n approaches infinity of 1 over n to the 0.5, but what is 0.5? 1/2, so that is square root of n. So this goes to 0. So that means that divergence test fail. Divergence test fails. So if the divergence test fails, we cannot say that it is divergent. That means we have to use a different test. So the good thing here is about, like, when you simplify, when you do this, you actually have an idea of which series you could compare this series to. So from here, it suggests that we can compare it to a series. So you can do comparisons test and then compare it to the series 1 over square root of n. So that series. And that is actually a p-series. So that is the same as 1 over n to the 1/2. So that is a p-series, which is with p equal to 1/2, that is less than 1. So that means divergent. Okay, so now we're comparing this to a p-series. So what you can do, instead of using a direct comparison test, we will use a limit comparison test. So we take the limit as n approaches infinity of, so the known series, which is n squared minus 3n all over the square root of n to the 5th plus 2, and then you divide that by 1 over the square root of n. Then this is equal to limit n approaches infinity of n squared minus 3n all over square root of n to the 5th plus 2 times, you get the reciprocal of this, which is square root of n. Then you distribute that to the numerator, to each term in the numerator. then and then you take the limit. So now as a shortcut, what we would do is we would just take the leading term, right? So this one would have n squared square root of n. That would be the leading term in the numerator, and then the leading term in the denominator would be the square root of n to the 5th, and then you simplify it. Now n to the 5th is also the same as n squared square root of n, which is just the numerator. So that is so that cancels. So what do you get? You get an answer of 1. So the limit is equal to 1, and that is greater than 0. So by the limit comparison test, the series is divergent. So now, if the series is divergent, it cannot converge. So therefore, 1 is not an option, and it also does not converge absolutely, nor it converges conditionally. So the only answer is letter B. Okay, now let's proceed to number 7. So we want to identify if this series is convergent, divergent, and then these are the suggestions: ratio test, divergence test, geometric series test, integral test. Okay, so now look at this expression. At first, you would always check whether the series is divergent using the divergence test. So what you would do is you take the limit as n approaches infinity of a sub n. A sub n here is tangent inverse of n. Now, take the limit of that. Now recall that the graph of tangent will be, it's like this, that looks like that. So this is pi over 2 and negative pi over 2. Okay, so this approaches to pi over 2 as n approaches infinity, and approaches to negative pi over 2 as n approaches negative infinity. So by the divergence test, this is pi over 2, correct? That is greater than 0. So that means it's divergent using the divergence test. So the answer is letter C. So this second choice here. Now for this next problem, we're asked to find the sum of the series. As I've mentioned, if you're asked to find the sum of the series, that is either a telescoping series or a geometric series. Then you look at the series here. Looks like this is a geometric series because, some terms is raised to n. Now you can write this in a geometric series form. Okay, so you could write that as n approaches infinity using loss of exponents. This will be 3 to the n times 3. Now, this will be 1/3 times the expression here, that is e over 3 quantity to the n. So now this is in the form summation a to the r to the n, which is a geometric series. So to get the sum, we have a formula. Okay, so we can get the sum of a geometric series if it is convergent. So is the series here convergent? So that is a geometric series, and with r equal to e over 3. And that is less than 1. And so that means it is convergent by geometric series. Definition of geometric series, or test for geometric series. So to get the sum, you have to follow the formula a over 1 minus r to the n. Or a stands for the first term. Okay, you use the more general formula wherein this is the first term And how do you get the first term? You just have to get a sub the first value for n there. And then r is the common ratio. That in r there is a common ratio. Common ratio. Okay, so again, the first term, a over 1 minus r. That is the formula for the sum, which r is the common ratio. So to get the first term, you will just have to evaluate your expression n when n is equal to 0. So this is e to the 0 all over 3 to the 0 plus 1. So that means this is 1/3. That's the first term. So you have 1/3 all over 1 minus, and then the r, the common ratio here, which is this one, e over 3. And then you simplify it. So you will have 1/3 all over 3 minus e over 3. And that is equal to 1 over 3 minus e. You flip the fraction here and then multiply that to the numerator. So that gives you letter D. So this next question is asking us to determine whether this series is absolutely convergent, conditionally convergent, or divergent. Now I want you to remember the definition of conditionally convergent sequence. Conditionally convergent is a sequence wherein it is convergent as is, Normally, if if it is an alternating series, you will have to determine convergence using the alternating series test. Now, if that turns out to be convergent, then we know that the series is, that series is convergent. But then when you take the absolute value of the series and then you determine the convergence of that series, and you find out that that series is divergent. Okay, so if the absolute value is divergent, then that series is conditionally convergent. Okay, so that's the definition of conditionally convergent. Series is convergent, but its absolute value is divergent. Now, absolutely convergent means the series is convergent. So if you take the absolute value of the series and then you determine convergence and you find out that it is convergent, then it's convergent absolutely. It implies convergence. Okay, so let's work on this series. So first, we might want to find the absolute value. Let's check first. If you take the absolute value and you get a convergence, the absolute value is convergent, that means the series is absolutely convergent. And then if it's absolutely convergent, the series is convergent. But then if we get a divergence, we might get conditionally convergent. So we'll have to do another test. Okay, so it's better to get first the absolute value. So let's take a look at the absolute value, a sub n, and then absolute value of this a sub n here is just 1 over n times ln n. And to proceed, we'll think of ways in how we can, check for convergence here. I would suggest using integral test, because if you let u be equal to ln n, your du is just 1 over n dn. So in other words, I can just take the limit n approaches infinity of 1 to the infinity, 1 to the n, 1 over u, and then du. Now, why can I use integral test here? I could also use integral test here because it's obvious that this term here is non-increasing. Okay, so it's decreasing because the numerator is just constant, and then the denominator is the denominator is increasing. And also, we know that these are all positive because n starts from 2 up to infinity. All right, so that means all of the conditions for integral tests have been checked. So I could use that. Now, I'll integrate that. That is equal to ln. So limit n approaches infinity. So this one, integral of 1 over u is ln u. And then you will have u evaluated from 1 to n. So this is equal to limit n approaches infinity of ln of n minus ln of 1. But what is ln of 1? That is just 0. And ln of infinity is also infinity. So that means it is divergent. So again, that's for the absolute value. So the absolute value is divergent. So we can't say at this point that the series is divergent. Letter E is inconclusive yet because we just looked at the absolute value. So now let's take a look at the series without getting the absolute value because we might get conditionally convergent. Now the series here is an alternating series. So we could use the alternating series test to do that. So use alternating series test to determine convergence for the original series. Now, all you need to do is take the limit, right? The limit as, where would I write that? So alternating, so this is alternating series test. I'll take the limit of the series 1 over n, and n approaches infinity. Okay. That is equal to 0 because the denominator is infinite, right? Oh, I could fit that here. So I take the limit n approaches, because a series is alternating, it is also decreasing. You just have to take the limit of a sub n without the negative 1 to the n, and then let that approach to infinity, and that this approaches to 0 because the denominator here approaches to infinity. Constant over infinity approaches to 0. So if it is 0, we know from the alternating series test that it is convergent. So by alternating series test, this is convergent because we got a 0. So we have a series wherein if you take the absolute value, it is divergent, but without the absolute value, it is convergent. So we call that series a conditionally convergent series. So similar to the previous problem, we have this same question here. We are to determine whether the series is convergent absolutely, conditionally, or divergent. Again, if it is convergent absolutely, it is also convergent. So if this is true, this is also true. But what is converges conditionally again? It is convergent as is, but then if you take the absolute value, it is divergent. So what we normally do is we take the absolute value of the series first. So we take the absolute value of a sub n, and that is equal to 1 over 2n plus 1 factorial. That's the absolute value. And then you can determine convergence of that. So if there is a factorial, because of that factorial, you will have to use the ratio test. Always, right? If there is a factorial, you would have to use ratio test. So now you will have limit n approaches infinity of 1 over a sub n plus 1. So that means you have to replace your n here by n plus 1. So 2, and then you put parentheses, because if you don't, you're only multiplying 2 to n, right? So you have n plus 1. So the n plus 1 is multiplied to 2. plus 1 factorial divided by the denominator is a sub n. So that's 2n plus 1 factorial. Now, this is equal to limit n approaches infinity of 1 over, then you simplify this. That is 2n plus 2 plus 1 factorial. And then times 2n plus 1 factorial. Now, what does this one means? 2n plus 3. So this is actually 2n plus 3 factorial. Then let's expand that. So you have limit n approaches infinity of 2n plus 1 factorial divided by 2n plus 1, so starting at 1 factorial. Then the remaining terms will be 2n plus 2, so you keep on adding 1, so 2n plus 3. That's the definition. Then that cancels out. So you're left with 1 over this expression here, where this goes to 0, because this one will just be, the denominator goes to infinity. That denominator goes to infinity. The numerator is just 1, so that is 0. So what do we see here? Absolute value, it is 0. This is absolute value of this, and we actually use the ratio test, not root test. So, and for ratio test, if this is less than 1, then that means it is convergent. So we got 0 and that's less than 1, so that means it is convergent. So if it is convergent, absolutely, because that's the absolute value, that means 1 is correct, and absolute convergence implies convergence. So 1 and 2 are the answer. So 1 and 2, letter D. Yeah, for number 11, we are asked to find a ratio test. So ratio test is this test here to determine whether the series is convergent or divergent. All right, or inconclusive. So you look at the conditions for ratio test. Okay, so to do that, let's set up our expression. So you have limit of a sub n plus 1. So you have 8 to the n plus 1 divided by n plus 1 to the 6th all over a sub n, 8 to the n over n to the 6th. So take the limit as n approaches infinity. Then you simplify this using loss of exponents. The numerator, this is equal to 8 to the n times 8. And then the denominator, that is just n plus 1 to the 6. No need to expand it. Times. Then get the reciprocal of the denominator. So that is n to the 6th all over 8 to the n. Then that cancels. So you have n to the 6th over this, so limit n approaches infinity of 8 n to the 6th all over n plus 1 to the 6th power. Or you could also write that as limit n approaches infinity of 8. You could take out the 8, and then you will have n over n plus 1 to the 6th. Then you could put the limit inside here using properties of limit. So then you compare the degrees of numerator and denominator. That the one inside actually goes to 1. 1 to the 6th power is just 1. So this is equal to 8. So it's 8 times 1, and that is equal to 8. So the answer is the limit as n approaches infinity of the expression here is equal to 8. Those two could be the answer. But what is the conclusion? 8 is greater than 1. If it is greater than 1, the series is divergent. So this is the answer. So again, by ratio test, if the limit of the ratio here is greater than 1, then the series is divergent. If it is less than 1, the series is convergent. And then if it is equal to 1, the test is inconclusive. Number 12, we are to apply the root test to the series and then find the conclusion. So to do this, we are going to get the limit of the nth root of the absolute value of negative n over 2n plus 1 raised to 3n. Absolute value of that expression. Now, you may take out the negative here, right? This means you could factor out that negative 1 because you will have negative 1 to the 3n. So when you take the absolute value, this is just equal to the limit and approaches infinity of the nth root of n, so that becomes n, positive n over 2n plus 1 to the 3n. Okay, now let's simplify this. That means we actually can divide the power here by n. So this is equal to the limit n approaches infinity. You could write this as n over 2n plus 1 to the 3n. Then you raise that to the 1 over n. Now the n cancels out. So we have a cube here. Then by the property of limit, we can have limit of n over 2n plus 1 cube. You could put the limit inside. And what do you get here? Comparing the powers, the degrees in the numerator and denominator, they're both equal to 1. They have the same degree, so you can just cancel that n. The one inside actually approaches to 1/2. So therefore, and then you raise that to the power here. You copy that power. So you have 1/2 cube, and that is equal to 1/8. So, but there's no answer here. The answer should be 1/8. Positive 1/8. And that means if positive, so sometimes there's an error. We make sure that on the test there's no error. So and the answer here is actually 1/8. And then that means if it's 1/8, that means it is less than 1. If it is less than 1, the series is convergent. So the series is convergent. So let's just remove let's remove that. And that should be the answer. Number 13. The question here is that which of the following is a valid argument for convergence or divergence of the series? Now, looks like we are comparing the series. So let's look at the direct comparisons test. So you look at the choices and see what are we trying to accomplish here. We're trying to use a direct comparison test. So now let's take a look at this series here. We could compare this series to the series 1 over n plus 1. Okay, so you compare that. Now, this series, the numerator is increasing. So that is greater than 1 here. So that means that this series is bigger than this series. So it is contained, this series actually contains this series. Right, so we could say that 1 over n plus 1 is less than or equal to ln n over n plus 1. So as you notice, they have the same denominator, different numerator. So, but the numerator here, ln n, is greater than 1. Next, let's determine the convergence or divergence of the series here. This series here, 1 over n plus 1, is like a harmonic series. So you could actually rewrite this series. So first, this is n equals 1 to infinity. You can reindex that to rewrite this 1 over n plus 1 as 1 over n. So by reindexing this, notice that from n plus 1 you want it to be n. So that means you subtracted 1 here to make it to n. So if you subtract 1 here, then you would have to add 1 to the limits of your summation. So you would have n equals 2 to infinity. Now you could try by plugging in. If I plug in n equals 2 here, the first term will be 1/2. If I plug in n equals 1 here, the first term would also be 1/2. So those two series are actually equal. You just reindex this series to make it look like this. And now, by looking at this series, we know that this is a harmonic series. And a harmonic series is a divergent series. So we are comparing the original series to a harmonic series, which is a divergent series. And then by the direct comparison test, if that known series, the known series, when I say known series, the convergence of that series is known. So we're comparing it to a known series, and that known series is divergent, and that series is contained in the given series, then that series is divergent. So by the direct comparison test, the series is divergent. Okay, so now if we look at this, we have this is less than that, right? For n starting at, so as long as it starts at, it contains the n here. So now n here starts from 1 to infinity. So it doesn't matter if it starts at n greater than or equal to 3. And then this one is divergent. Okay, so that's the answer. Okay, so for number 14, we are to determine whether the series is convergent or divergent. Now, if you look at the choices here, looks like you're either going to use the comparisons test or the limit comparisons test. So here, we just want to know which statement here is true, if you're going to use either the comparisons test or the limit comparisons test. Now, you examine the limit here and see where you could actually you could compare these two. Now, to do that, you can look at the expression here, and then you can simplify that. So you have 1 over the square root of n squared. That would simplify to 1 over n. And if you're going to compare it to 1 over n, that series, this is a harmonic series, and that is divergent. So if you are going to use a comparisons test, you have to prove that this series is less than the series here. Okay, so you would have to prove that. Now, because it's a little bit harder to prove. No, you would just have to do that later. Okay, so you would try to do the limit comparisons test first because that's a lot easier, and see if this of the statements here, either of the three statements here, is correct. Okay, so if you use the limit comparisons test, all you need to do is take the limit as n approaches infinity of 1 over of a sub n, which is 1 over square root of n squared plus 4, divided by the limit that you're trying to compare this to. So the limit with known divergence. So we have 1 over n. And then you simplify this. You have limit n approaches infinity of 1 over the square root of n squared plus 4 times n over 1. Now, this would be equal to the expression here. Then let's go ahead and then evaluate this. To evaluate this, we will just have to divide this by, or multiply this by 1 over the square root of n squared. The square root of n squared all over 1 over the square root of n squared. Then this is equal to, now remember, the square root of n squared, the square root of n squared is equal to the absolute value of n. And when we say absolute value of n, that is equal to n when n is greater than 0. And it is equal to negative n when n is negative. That's less than 0. So so that means that here, since n here is positive, because n approaches to positive infinity, this square root of n, which is the square root of n squared, which is absolute value of n, will just be n. So that numerator will just be 1. Okay, so here, n times 1 over n. And we replace this square root of n squared by n, because our n here approaches to infinity. But the denominator, we will divide each term here by n squared. So you'll have 1 plus 4n squared. That cancels. This goes to 0. So what's the answer here? The answer here is 1. And 1 which is greater than 0. So by the limit comparisons test, the convergence or divergence follows along the series that you use to compare it to. So since we compared it to a divergent series, then that means that the series is also divergent. The series is divergent. Okay, so now let's look at the statements here. The series diverges by limit comparisons test, and you compare it to this. Yes, that's the answer.